Welcome to the class of dual simplex method for a linear programming problem. Consider a linear programming problem subject to ax equal to b, x greater than or equal to 0. Suppose this problem is in standard form and we know that we can solve this problem by using simplex method, right? And typically an optimal solution of this problem has the following form in the simplex tableau. You can see this is the simplex tableau. Suppose we have n variables x1, x2, here xj, xn, and these are my basic variables xb1, xb2 up to some intermediate variable xbr and xbm, m variables, and we know these variables are non-negative in the optimal simplex table. And this is my zj minus cj row. They also are greater than or equal to 0 because we know that zj minus cj are greater than or equal to 0 for a maximization problem. So these are my, say, zj minus cj. So this is my typical simplex table. But sometimes we have a situation like we have the optimality declared but the feasibility is disturbed. Feasibility is disturbed. What it means, the feasibility is disturbed. So that means for some rth variable, this I have a, this variable is negative, or I should write in this form that my rth variable is basically negative in the optimal simplex table, right? And the optimality is declared. So now this is a situation when we have a basic solution which is optimal but it is not feasible. But we, for this problem, we want to find a feasible solution because all the variables need to be greater than or equal to 0. So this table does not actually give the optimal solution of this problem, although zj minus ej's are greater than or equal to 0. So we need to have these basic variables also have the non-negative values. So here comes the dual simplex method to rescue. So simplex method will not work, right? So what we do, we work with the dual simplex method. Dual simplex method. So what does dual simplex method says? It says that we can obtain an optimal solution of this problem. Optimal solution of this problem means that zj minus ej's are greater than or equal to 0 by retaining this feasibility. So what dual simplex method do is it will retain feasibility, maintaining optimality. So please remember these things. So what we are going to do is we will maintain the optimal solution or optimality condition, but we will reach at a basic solution which is feasible also. So we are going to handle this negativity. So to obtain optimal basic feasible solution, first we would like to get rid of this negative variable. So what dual simplex method do, it chooses this negative variable, rth basic variable, to go out of the basis. So first we are choosing a leaving variable. So how leaving variable is chosen, that you choose that basic variable xbr, which is like what, minimum of the xbi, such that xbi is less than or equal to 0 for I less than or equal to m greater than or equal to 1. So that means out of all the basic variables, the one which is most negative, we will choose that one to leave the basis. So in dual simplex method, we are first choosing the leaving variable, then we will be choosing the entering variable, right? The criteria is reversed from the normal simplex method. So please note this thing. So the leaving variable is chosen xbr out of those basic variables which is most negative. See, in this case we are seeing only one negative variable, but there may be more than one negative variables. So out of all those variables we'll be choosing the one with which is most negative. Then how we are going to choose the entering variable? So for entering variable, we know the alpha j's for this rth row are what? Alpha r1, alpha r2, alpha rj up to alpha rn. I'm not writing the columns, but I only need this and the information of this row. So for entering variable, we have zk minus ck upon alpha rk. It is equal to, we have to choose that for which it is zj minus cj upon alpha rj with alpha rj less than 0. Okay, so let us take this variable as the kth variable. So we are going to choose that kth variable. Instead of writing j, I write it as k. So we will choose that kth variable to enter into the basis for which this criteria is satisfied. And what is this criteria? We take the ratio of zj minus cj with alpha rj, like this is z1 minus c1. We take this ratio with this one. We take the ratio of zj to z2 minus c2 with this, and so on. But not all of the alpha rj have to be taken. Only those alpha j's have to be taken which are strictly negative, right? So remember, in case of dual simplex method, since we want to get rid of this negative variable, so first we are deciding the leaving variable, then we are deciding the entering variable. The criteria is reversed from the normal simplex method. In the simplex method, we were choosing the entering variable first and then the leaving variable, but here things are reversed. Let us understand this thing by means of an example. So consider the following problem. Minimize 3x1 plus 5x2 subject to 2x1 plus x2 greater than or equal to 0 minus x1 plus x2 greater than or equal to 1, 3x1 plus 2x2 less than or equal to 6, x1 x2 greater than or equal to 0. Also please note one more thing, that this criteria which we have written here, it works both for the minimization problem as well as for the maximization problem, because we are taking the modulus of the values here. So even if it is minimization problem, so here I have taken a maximization problem. Even if it is a minimization problem also, the same criteria will work. You see, in this example we have taken the minimization problem and we will use the same criteria to obtain our optimal basic feasible solution. So how we are going to do this? So firstly, we don't want to write this problem in the standard form because we want to apply the dual simplex method as the situation demands. So let us write this problem in this way. This is minus 2x1 minus x2 less than or equal to minus 2 minus x1 plus x1 minus x2 less than or equal to 1, 3x1 plus 2x2 less than or equal to 6. So these are my three constraints. I am multiplying the first two constraints by the minus sign. Now again I want to write it in the equation form as I need to add the slack variable. So my problem becomes minimize 3x1 plus 5x2 plus 0s1 plus 0s2 plus 0s3, which are s1 s2 comes in these constraints, 2x1 minus 2x2 minus x2 plus s1 is minus 2, x1 minus x2 plus s2 is minus 1, 3x1 plus 2x2 plus s3 is 6, x1, x2, s1, s2, s3 are not getting. Now let us construct a table by taking s1, s2, s3 into the bases. So I am writing a simplex table corresponding to the basic variables s1, s2, s3. You see, if s1, s2, s3 are the basic variables, I have the identity matrix here. So what are my alpha j's? x1, x2, s1, s2, s3. So my first table becomes, because these are the identity columns, so my alpha 1 first column is same, minus 2, 1, 3, minus 1, minus 1, 2, 1, 0, 0, 0, 1, 0, 0, 0, 1, and the right hand side is minus 2, minus 1, 6. And what are my zj minus ej? If you write cb, these are my 0, 0, 0. So my zj minus ej's are minus 3, minus 5, 0, 0, 0. Now you see, this table is optimal because all the zj minus ej's are negative here. See, this value is negative, this value is negative, right? But this table is not feasible because my two basic variables are negative. So now the normal simplex method cannot work, so we need to go for the dual simplex method. So dual simplex method, if you can recall, we first choose the leaving variable, and the leaving variable is one in which out of all the basic variables, which is the most negative. So which one is the most negative variable? It is minus 2 and minus 1. So what is the most negative? Minus 2. So we will choose minus 2 to leave the basis. And then how will you choose the entering variable? So out of all, in this row, out of all the alpha rj's, so we are going to find minimum of the value of what? Z1 minus c1 upon the negative of this. So minus 3 upon minus 2 mod, what is second? Minus 5 upon minus 1. This value is positive, this is 0, 0, we are not taking this. So what is the minimum value? So this implies we have to take minimum of 3 by 2 and 5. So what is the minimum? Minimum comes out to be 3 by 2. So what is the entering variable? Entering variable is my x1. Okay, so we have taken the modulus here. Okay, even if this is a maximization problem, so we again have to take the minimum of these values, right? In that case, we had this zj minus ej's are positive. Okay, now further, now we are applying the normal pivot operations, like we divide the whole row by minus 2 and then we will apply the row operations. So let us construct our next table in the usual way. So what is my next table? So my x1, x2, s1, s2, s3. So my basic variable becomes x1, s2, s3, and my table becomes 1, 0, 0, 1 by 2, minus 3 by 2, 1 by 2, minus 1 by 2, 1 by 2, 3 by 2, 0, 1, 0, 0, 0, 1, and my solution becomes 1, minus 2, 3. Okay, and my zj minus ej's are 0, minus 7 by 2, minus 3 by 2, 0, 0. Now you can see again here my Zj minus Cjs are all less than or equal to 0, means optimality is maintained, and one of the variable becomes positive. This one, it was negative here, so out of two variables we have made one positive, but still this is not an optimal feasible table because one of the basic variable is still negative. So what we have to do, we have to apply again the dual simplex method. So what we are going to do, we have to choose the leaving variable again. So what is a leaving variable? Because only one of the variable is negative, so this variable will leave the basis. Then which one is going to enter? Because these two are the positive value, only this is the negative value, so x2 is going to enter the basis. So we construct the third table. So what is my third table here? Third table becomes x1 x2 s1 s2 s3, and what are my basic variables now? x1 x2 s3. We have to apply the usual pivot operations, nothing new. We are all aware about that. 0 1 0, minus 1 by 3, minus 1 by 3, 5 by 3, 1 by 3, minus 2 by 3, 1 by 3, 0 0 1, 1 by 3, 4 by 3, 7 by 3, 0 0, 8 by 3, minus 7 by 3, 0. Now you can see in this table my Zj minus Cj are all negative. For the minimization problem, this indicates that this present table is optimal. Also my basic variables are all greater than or equal to 0, so it indicates that I have obtained a optimal basic feasible solution. So now dual simplex method has given me a optimal and a feasible solution. You see in the earlier tables, everywhere this table was optimal, this table was optimal, but these two tables were not feasible. Okay, so we moved from infeasible solution to feasible solutions maintaining optimality. So what we did, we moved from infeasible, I should say basic solutions to feasible basic solutions maintaining optimality. So the moment, since every table is optimal, the moment we obtained a feasible basic solution, since it is optimal also, so we obtained an optimal basic feasible solution. So this is how dual simplex method helps us to obtain the optimal basic feasible solution. Now we will discuss one more example where we will see that it also tells when this dual simplex method also give us the indication of an infeasible solution. So you consider the problem, minimize z equal to 3x1 plus 5x2 subject to 2x1 plus x2 less than or equal to 2, 3x1 plus 2x2 greater than or equal to 6, x1 x2 greater than or equal to 6. So this is my problem number 2, right? So again we write the problem in the usual form because I want to apply the dual simplex method, so I need to construct the second constraint. I need to multiply the second constraint with minus sign, and then I will add the slack variable and we'll see what my next table becomes. So that is, so the problem becomes minimize 3x1 plus 5x2 subject to 2x1 plus x2 plus s1 is equal to 2 minus 3x1 minus 2x2 minus s2 x1 x2 s1 s2 greater than or equal to 0. So we have 0 s1 plus. So I have written straightforward after multiplying this constraint by minus sign and this. You must note one more point here, that dual simplex method is applicable only when we have a infeasible solution which is optimal. So if we have an infeasible solution but it is also not optimal, dual simplex method does not work. Okay, let us check whether it satisfies the conditions of dual simplex method. Okay, let us see. Construct the table by taking my basic variables as s1 s2. So this becomes 2 minus 3 1 minus 2 1 0 0 1 2 minus 6, and my zj minus cj are minus 3 minus 5 0 0. You see again that zj minus cj are less than or equal to 0 because the problem was again minimization problem, and this is a infeasible solution. So since the problem is infeasible, since this table is infeasible but optimal, so dual simplex method is applicable here. Okay, so we can apply the dual simplex method. So what dual simplex method does here is, so what we do, we choose the leaving variable first. So my leaving variable is this. So first we will remove this out of the basis, and then what is the entering variable? We take minimum of minus 3 upon minus 3 mod, comma minus 5 upon minus 2 mod. So this is what, so the minimum values are 1 and 5 by 2, so minimum is 1. It comes at x1, so my x1 is the entering variable. So what is my table? My new table becomes x1 x2 s1 s2. So by basic, so it is s1 and s2 is replaced by x1. Okay, so my table becomes 0 1 minus 1 by 3 2 by 3 1 0 2 by 3 minus 1 by 3 minus 2 2, and my zj minus cj row is 0 minus 3 0 minus 1. Again this is an optimal table, but still this is infeasible table. Okay, let us again apply the dual simplex method. So what is my leaving variable? My leaving variable is this, the most negative one. So this will leave the basis. Then who is going to enter? So minus 3, so only one of the component here is negative, other are not eligible, so x2 is going to enter. So s1 will be replaced with the x2. So what is my next table? So my next table becomes x1 x2 s1 s2. So what are my basic variables now? So x2 x1 0 1 1 0. So again we are doing the pivot operations. Divide this row by minus 1 by 3 and then make this 0 by applying the row operation. Same way we are doing in the normal simplex method. So this is minus 3, 2, minus 2, 1, 6, minus 2. And what are my Zj minus Cj? It is 0, 0, minus 9, minus 7. Again, we have a optimal table which is not infeasible. So again, we would like to apply the dual simplex method. But you see here in this case, my leaving variable is minus 2. But in this row, you see all the entries, these entries are positive. You see, so all the entries are positive. So but in order here we have a leaving variable, but in order to have an entering variable, so the ratio must be negative. So we have to have alpha as negative, but none of the alpha is negative. That means this variable cannot be removed. So this is the best we can do. So this indicates that my above problem is infeasible. That means this infeasibility cannot be further removed. So we had this infeasibility, we came to this and to this, but there is no more further way to remove this infeasibility. So whenever there is a situation that alpha r's are all positive, this alpha r j are all positive for all j, this indicates infeasible solutions in a dual simplex method. Okay, so this indicates infeasible infeasible solution. Okay, so you remember one thing. So dual simplex method is applicable only when we have a simplex table which depicts an optimal but infeasible solution. So always remember, it is applicable when we have these two conditions, that the basic solution should be optimal but infeasible. Okay, so in case you have non-optimal, non-feasible solution, dual simplex method is not applicable. Okay, so always remember that dual simplex method is applicable only when we have an optimal but infeasible solution. So in this case, it is not applicable. Okay, thank you for watching.